In the previous part, we looked at the one-time pad and perfect ciphers. And in particular, we looked at the requirement for perfect secrecy, which is that your key length has to be greater or equal to the message length. And this makes the use of a perfect cipher very hard in practice or even impossible. The ideas behind a one-time pad are pretty good though. So this is where stream ciphers or Q ciphers come in. So the idea behind stream ciphers is that could we take the good working principles of the one-time pad and make them more practical. These good features, if we remember back to last time, were that the encryption is very good, it indeed is perfect, encryption is very fast, but the key length is somewhat impractical. So if we think about this, only this last requirement, the key length, is something that needs to be fixed in order for this to be useful in the real world. So could the key be shorter? So what if we replaced a truly random key with a pseudo-random key? To produce pseudo-random numbers, we need a pseudo-random number generator or a PRG. Now, a pseudo-random number generator is a function, let's call this function g, that has a particular seed, or takes in a particular seed here and produces a bit stream based on that seed. And crucially, the length of the bit stream is much larger than the value of the seed. If we use this seed value as a key, we could say that in a stream cipher, the key is short, but the bit stream needed to decipher the message or cipher the message is still going to be as long as the message itself. So that would mean that encryption and decryption is still easy and still fast, but we just replace the truly random long key required by the one-time pad with a pseudo-random number generated by the pseudo-random number generator. So in essence, the idea of a stream cipher is very simple. Instead of having this long key, we modify this formula a little bit so that the encryption algorithm is now the message M XORed with the result of the running a pseudo-random number generator G with a short key K. Decryption works similarly, so we take the ciphertext and the same key, same short key that was used to cipher the message, and we should get the original message M back. So in essence, what we're doing is we take some short key K right here and simply expand it using a pseudo-random number generator G here, so that as a result we can still use the same principle of the one-time pad to encrypt our our plaintext message into a ciphertext. So using a stream cipher, it's possible to make the one-time pad practical. However, there are some considerations. The stream ciphers are not perfect, so we're going to need better definitions for security than the requirement for perfect secrecy. And in fact, the secrecy or security of the stream cipher is dependent on the security of the pseudo-random number generator. In practice, the security requirements for a random number generator boils down to one. The pseudo-random number generator must be unpredictable. What I mean by this is basically, well, let's imagine we have the generator and we know the value, or we calculate the value for some n. Then we should not be able to make any deductions about what that generator would produce based on, let's say, n+1 and so on. So based on one value, we shouldn't be able to figure out what the remaining values or remaining bits are. And there is a very good reason for this requirement. So let's presume that an attacker has secured some portion of unciphered text. Maybe it's based on a guess, maybe it's based on knowledge. In real world, this is not so difficult to do, because for instance, we always know that emails start with a from header. Or we always know, or we could guess, that World War II German messages ended with Heil Hitler. If we then think of the bit stream that the pseudo-random number generator generates, well, by definition, the random number generator is unpredictable if we cannot predict what the resulting bit stream is. That is, even if we know what the bit stream was in the beginning, then we shouldn't be able to predict what the following values are going to be. So in our example, let's say we have secured a ciphered email message. So we probably know that the beginning of that message is going to be the from header. So it's going to say from somewhere in the beginning of the message. Now, why can this be problematic? Well, let's consider the formula for the one-time pad, or how to secure messages in the first place. So using a random number generator, we had the formula like this. So m XORed with whatever the random number generator produces is going to be equal to the ciphertext. Now, XOR, or exclusive OR, is an associative operator. So it also stands that GK XORed with C equals the message, and crucially M XORed with C equals the GK, or the output of GK. So if we consider here, what do we usually see as the attacker, or as an outsider? Well, we should only be able to see the ciphertext C, but if we can guess the message, or if we can guess parts of the message, then we also know what M is. So then, based on this formula, it's pretty easy to figure out what, well, we can calculate what GK is, or parts of what GK was. So in essence, if we can guess parts of the message, we can then find parts of the key. And if we can guess a part of the message, we can find a part of the key as well. And if this happens, then we better not be able to find the whole key if we know parts of the key. So from here, if we can figure out this portion of the generated key, it would be really bad if we were able to use that information in order to figure out what the rest of the key was here, or at least the next section of the key here. So that's basically the problem, and the reason why the pseudo-random number generator really needs to be unpredictable. Finally, there are some known weak pseudo-random number generators that we really should not use for the purpose of encryption. So first, there's the linear concurrential generator, which is basically just a formula that calculates new random numbers or pseudo-random numbers based on some previous seed value. If we look at this formula, we can pretty quickly see that n+1 and n are quite closely related to each other. So Rn and Rn+1 are dependent on each other, and this is not in accordance with our requirement for the random number generator to be unpredictable. In addition to this, operating systems also provide an interface for generating random numbers. On a server side, so in practice on Linux and Unix systems, we have something called a random function, which comes with the glibc library. And on Linux and Unix systems, there's also a system device called /dev/urandom, which is capable of generating some pseudo-random numbers. But these are not random numbers that you could use for encrypting data, because they suffer from the same problem as the linear concurrential generator, in that the random numbers generated are not completely independent of each other.